It's my pleasure to introduce you Professor Emanuele Rodolà from Scienza, University of Rome. He's a full professor, and also he is the winner of a ERC studying grant, which is very prestigious grant. So today, I think our professor will share with us his interesting research findings in terms of geometric deep learning, and also his very valuable experience in terms of how to become this winner of this grant, and also being a PI. Okay, I will leave the stage to Professor.
Thank you. Can you hear me well from behind? You hear me well? Yes. All right. So to begin, feel free to interrupt me if you have doubts, questions, curiosities. Just ask. Okay, just shoot. No problem. So I would like to tell you a couple of things. I have two, I believe, valuable lessons for you. So the first one, lesson one, is build your own path. So you are PhD students, postdocs. What are you? PhD professors, I believe. Postdocs? Yes. You're a postdoc? Yes. All right. So I think this is a lesson that is good for all of us, so at all academic levels, not only PhD students. Try to interpret what I tell you in terms of your current academic age. Okay? So build your own path. What does it mean? Well, let me give you an example. So, well, you recognize this is the planet. So I want to show you what was my path. And I want to tell you a couple of things of what went well and what went wrong. Okay? So first of all, well, I graduated in computer engineering in Rome, not Scienza, another university, Then I did my PhD in computer science in Venice. And then during my PhD, I spent a couple of months at Technion in Israel. So this is something that you PhD students should do now. So I believe you have the opportunity to spend a research period somewhere else during your PhD. Is that right? You're in Trento as well. Do it. So by all means, do it. So in Venice at the time, we didn't have too many funds. So like we had 0 funds. And I really wanted to do this experience. So I decided to put my own pocket money for everything, like for 2 months of apartment in Israel, for the flight, for conferences in Israel, so my own money, so out of the PhD salary. So and I think that's the best choice I ever made. But so this is where you start building your path. So by all means, do it. I will come back to Technion in a second. So after the Technion, I went for a period, a few months, at the University of Tokyo. That was my first postdoc experience. So this is where things started going wrong. Okay, so maybe you know, the University of Tokyo is a prestigious university. So one of the top in the Far East. I think Tsinghua University is another top venue in the Far East. Now the problem of the University of Tokyo is that I just wanted to go to the University of Tokyo. I didn't know anybody there. I didn't know what they were doing. I didn't know the kind of research they were doing. So I was there for all the wrong reasons. Okay, so this is a big mistake. I spent several months there doing something that I didn't like, or talking to people that were not interested in my research area. But that was a big mistake. Now, I think an interesting lesson here is that even if you find yourself in an uncomfortable situation where you feel alone and you don't have anybody to talk to, you don't have anybody contributing or like interacting with you or doing your own research, well, you have to learn something. You have to learn doing things alone. So that's the first key thing. You have to build your own ideas. You have to implement everything yourself. You have to convince the university that this is what you're doing is worth doing. So this was a very strong lesson for me. And of course, what I learned there made me a very good postdoc for the new positions. So after that, actually, there is a nice story here. In the streets, in the streets of Tokyo, actually in a bar, I met a German guy from TU München, from the Technical University of Munich, and he was working on my research area, and he told me they were looking for postdocs. So I met him in a bar in Tokyo, and so I said, okay, I'm going to cancel University of Tokyo and I'm coming to Munich. So this is what I did. So my next postdoc was at Munich, and so it was in an area different from mine once again, but somehow I convinced the professor, Professor Daniel Kranitz, if you heard of him, that there was the need to do what I was doing. So that was shape analysis research. And I was feeling very confident that I could do it alone because I had been doing it alone all along, right? So that was very good for me that I had such a bad experience in Tokyo. Now, when I was at Technion, well, not Technion, the Technical University of Munich, I published some interesting stuff that put me in contact with another professor, Professor Michael Bronstein from the University of Lugano, so in Switzerland, and he invited me to spend some time at as a postdoc, so a couple of years at the University of Lugano. And during all these traveling around the world, I had the opportunity to do a lot of research visits, in particular self-invited research visits. So that's a trick that you should learn. So you should go to like prestigious. So I'm just listing two of them, but I self-invited myself to several places all around. Okay? So that's a very good trick to say, Professor X, I will be in Stanford for a couple of weeks. It would be cool to meet up. Maybe I can give a talk, and then he or she will say, oh, of course, please come. So you should self-promote. So we come back to this point. Okay? Otherwise, I mean, nobody is going to look for you, right? So if they don't know you, they're not going to look for you. So either you write a super popular paper that everybody knows about, or nobody is going to look for you. So you should make yourself evident. Okay, so this is more or less my path. Then while I was in Switzerland, I decided I wanted to come back to Italy. So if you guys are Italian, this will happen to you. So you will travel all around, and then after, I don't know, 5, 10 years, you will say, I want to go back to Italy. So I decided to go back to Italy, and then I won a professor called at Scienza, which is where I am now. Okay? So I didn't put this on the map. All right, so a few key things I would like to share with you. From all this traveling, what I got? Well, first of all, I changed my research topic all the time. But all the different places over here, I changed topic. So what I did during the PhD is not what I'm doing now. Okay, so during the PhD in Venice, I was doing 3D reconstruction. You know, now we have the Kinect, we have the 3D camera inside the laptops. At the time, we didn't have those. So at the time, you really had to build your own technology to do 3D reconstruction. So I was doing that. Then when I moved to the University of Tokyo, I was doing robotics. So they do a lot of humanoid, robotic vision. So something different from that. When I was at Technion, I was made aware of an area called shape analysis. So then I decided I want to do shape analysis. So I brought shape analysis to Munich. Then in Munich, I met spectral geometry. So I decided I want to do spectral geometry. And when I was in Switzerland, I met geometric deep learning. So actually I was there when geometric deep learning was invented by my advisor. So I changed the domain a lot of times. So and that really valuable. Why? Because it makes you very unique. So you didn't do the path that everybody did. Like people doing, I don't know, semantic segmentation, maybe they only do semantic segmentation. So that makes you the same as other people doing semantic segmentation. So if you really want to differentiate yourself, if you really want to highlight your positioning on the map, you want to be quite unique, And also you want to have like a heterogeneous background. You want to build bridges across different areas. Okay? So that was very valuable for me. So now I find myself being expert in nothing, but I know a lot of everything. So that's very valuable, especially when you write grants. I will show you. Second thing, don't be afraid to change your mind. So while I was in Tokyo, I changed my mind a lot about certain things that I knew I liked. And then I said, well, I really don't like this. It was very difficult for me because at the time I had invested a lot of time doing 3D reconstruction, like years doing 3D reconstruction. And then I said, but I don't really like 3D reconstruction. So I had to be honest with myself. I have to change my mind about what I like. And then when I was in Switzerland, I hated deep learning because that was non-explainable. Right? You know, there is this tendency to see networks as black boxes that I really didn't like it. So I had to change my mind because eventually I came to like this technique that really solves practical problems. So I said, well, after all, I think I like deep learning. And actually, the fact that they are so difficult to explain makes them so interesting to study, right? So don't be afraid to change your mind. And I think this is the one that really applied to me the most. Don't be afraid to challenge dogmas. So what do I mean by that? So I don't know what to work on. There are several unwritten rules about what you're studying. I will show you an example of my area. Let me give you an example. Let's see. Okay, so there was this. So do you know early stopping as a technique for training neural networks? So there was this rule that tells you if you're training a network, you're tracking the validation error. As soon as it goes up, you stop. You stop training, right? So that's called early stopping. So that's a dogma for us. So who would ever keep training as the validation error goes up? Who does that? Did you do that? Did you try?
Sometimes.
Okay, and then what happens? Did you observe anything special?
Not in my case.
Okay. Okay, so if you insisted just a little bit more, you would see this phenomenon called double descent. So the validation error goes up, and you keep training, keep going up, keep training, and then at some point, boom, it goes down like crazy. So this is called double descent, one of the most important discoveries in deep learning in the last few years, like in the last 3 years. Okay? So, and who did this? Mikhail Belkin. He challenged the dogma that you should stop training when the validation error goes up. Okay? It's just an example out of my mind. I will show you a couple more. So don't be afraid to do that. There are no guarantees in deep learning in particular. There are no guarantees or very few guarantees. So you should feel free to experiment and to say the opposite of what Jan LeCun is saying. Feel free to do that. Okay? Finally, promote yourself. These I already anticipated. You want to go around and make yourself evident to the community. You want to say, I'm here, I'm doing this, I can give a talk, we can chat, this is my new paper. So I did this all the time. I was spamming my community with my new papers all the time. I mean, not like crazy. Like the few people I met at the conferences, it was nice to meet you. This is my new paper. I think it relates with your research. If you can give me some feedback, I would be happy to hear. Something like that. But you should promote yourself. Nobody is going to promote you. Right? So do it yourself. Okay. Now, ERC. Okay, so this is the first grant I got, actually. It was very surprising for me that I got it. The first trial, I didn't have any grants before that. So I found it very difficult to get it, but I thought it would be very difficult. But then my advisors at the time, they told me, Emanuele, you should go for an ERC. We think you have good chances. Okay, so I had to think, do I have what it takes to get an ERC? Okay, so let's see what kind of questions you should ask yourselves. Well, first of all, yes, I was encouraged. If nobody told me, I would have not done it. Okay? So I'm here to tell you, you should do it. You should try. But maybe now, or for PhD students, maybe it's too early. But after your graduation, 2-3 years tops, you should try to get an ERC or any other prestigious program. What you need to do, you have to reflect upon yourself. What does it mean? You should really try to be honest to yourself. You should look at what you've done until now in your career. You should see what are the points that make you unique, make you different from all the others in your community. You should be honest. If you realize that you are not unique, if you realize that you didn't do anything different from all the others, then, well, that's a tough blow to take. But at least now you know. At least now you know you should change a few things if you want to gain a lot. Okay, so you should, this is the most difficult step. You should really do a self-critical analysis of your career. So this is, do you know the imposter syndrome? No? So the imposter syndrome is something that happens actually quite frequently when you think you don't deserve what you have. So imagine you got prizes or your paper got accepted at New Rips, at ICML, and then you look at the paper and say, but maybe after all, it's not really worth it. Maybe after all, this paper is not really ICML level. So this happens, used to happen to me all the time. Sometimes it still happens that you think you are an imposter because you think you are not as valuable as other people say. So this happens a lot in our community. So you don't think you deserve what you have. Beware of this. This is very common. If you have what you have, it's because you deserve it. It's very easy. Usually, whatever we get it through a selection process. So we are evaluated against other people. So there is a selection process that you pass. If you passed it, then you are not an imposter. Other people, peers that don't know you, they judge you. So beware of this. Don't think you don't deserve things. Maybe some of you are thinking, I don't want to go for an ERC because I don't think I deserve it. That's imposter syndrome. Okay? So what you should do this reflection. You should identify weak points and so on. Okay, so what's the best thing to compare with the others? So I'm showing you my key statistics at the time that I applied for the starting line. It was 2018. Now, in my community, this is not very good. Okay, so I had less than 1,000 citations by the time I applied for the ERC. We all know that in machine learning at this academic age, which is 7-8 years of research, less than 1,000 citations is not so much, right? On the other hand, I realized that the path was exponentially growing, so that was a good sign. And also that I had a background that was very unique, as I told you already. And I had these self-invited visiting positions at prestigious places. Once they met me, they invited me several more times. So that worked. And I also had, you see, this Japan Society for the Promotion of Science and the Humboldt Fellowship. So those are 2 fellowships that I got when I got my first 2 postdocs. Okay? And I believe that that was quite unique in my area. Okay? So I compared myself with other people in my area with my same age in academic sense. And I said, okay, I have something more than that. So then I can apply. Okay, so this is what you should do. Don't do absolute evaluations. Don't just look at the number of citations and say, ah, I don't have what it takes. Okay, so it depends on your area, it depends on the rest of the background, and so on and so forth. Okay, so you should do this very carefully. Okay, actually, one reviewer, I remember one reviewer from the ERC wrote, compared to other scientists with the same age, he doesn't have too strong scores. So he actually wrote it explicitly. But he did this, and that. I had some best papers. So that really paid out. They paid out. Okay. Okay. So a few words on the career impact. I'm not sharing tricks on how to write a grant. I think it's too early. In general, you can ask me. So even if when I go back to Rome, I can share my grant with you. You can ask me for help. So the career impact is very, very strong. Well, first of all, if you get the ERC, you can work on your own things. So the things you wrote on the grant, you can work on them. And so one of the things they say at the ERC is that you have no strings attached. It means that you're free to do what you like. Nobody will ever tell you that what you're doing is not good, or nobody will ever tell you that you're not publishing. If you don't publish during the ERC, no problem. They're not gonna get the money back. Okay? So you're completely free. And if you have the ERC, you can attract the best talents to work with you, of course. So what happened to me? A few things. Soon after the ERC, I had the career advancement. So I became a full professor at Scienza. I got several other important fellowships. Like I became fellow of the School of Advanced Studies of the Young Academy of Europe, Ellis. Do you know Ellis? So all these things, I think these doors open, but once you have the ERC, it's very easy to open several doors. A lot easier than without. You become part of important strategic committees, not only at the university level, but also at the European and international level. You become a keynote speaker in several conferences. You get new grants much more easily. So basically, if you get it, you're done. You can retire. All right. So I think this sums up pretty well that you should go for ERC, and in general, you should really try to go for the difficult things that are perceived very difficult by others. That's exactly what you should do. That's exactly things that other people are afraid to address. This is where you come in. This is what you should do. Don't discourage yourself. You should always aim high. So that's the main thing I also tell all my students. Even when you have an idea for a paper, where do you send it? Do you send it to a minor conference where you're sure it will get accepted? Or do you send it to a very selective conference? Like I see a lot, where it's much less likely to get it accepted. Always aim high. Should always go for the most difficult one. Okay? All right. Questions on this part? Because I'm moving on to the research section. Yes?
Yeah. Is it to make professors convinced of changing the topic? But your topic for PhD will differ from how easy it is to make it.
So I didn't get the first part of the sentence, but so the question is, how easy was it for me to change topic, or for the professor to accept?
Yeah, to make professors convinced. I mean, when you have an interview, you the government why you change your topic, why you think it's successful in this area.
Okay, I see. So convincing the people interviewing you that it's a good idea to change direction is actually quite easy, because you are an expert on what you've been doing until now. So I was an expert of 3D reconstruction. then I said, I think 3D reconstruction stops being an interesting research problem because people are buying 3D cameras. So at this point, we can only do engineering, fine-tune a few things. I think it's much better to move to something unexplored. And I can show you, so I did very well here, I published CVPR, UCCBA, CCV. I can do the same with another topic. So the professor was convinced. If you do well in what you've been doing, then it's easy to convince. So there are some companies, well, I will not name them, but one of the questions they ask during the interview, if you want to enter this company, is, well, they want to actually understand that you are brave enough to change completely your company. So this is a value. Okay. All right. So lesson 2. Some of our research. So I'm going to cover a few things about geometric deep learning. I'm not going to go into the details. I'm not going to be technical, because I want to give you a few ideas of what are the main challenges, why it is interesting. At any point, if you want details, ask me. Okay? So you guys work on deep learning in general? Yes, all of you? Anything different?
No.
Deep learning? Anything different? Mathematics.
No.
What kind of mathematics?
Mathematical analysis and current evaluation.
Ah, nice.
Geometry.
Excellent, excellent. So I hope I have something for you, but I will not go into the details. Feel free to answer.
That's my experience.
Ah,
Something.
okay. All right. Well, success of deep learning. I don't think I have to explain the success of deep learning. I don't know if you remember in 2012. So there was this visual classification challenge, right? So I show you a photo of something. You have to tell me what's inside the photo. I show you a photo of a cat. The algorithm should tell me cat. So in 2012, there was this huge gap in accuracy, and that was when the first deep learning-based techniques for visual classification was published. And then you see in 2015, the machine learning-based algorithms are better than humans at solving this task. Okay, so this is what we call superhuman accuracy. Okay, so it is already part of commercial technology, autonomous cars, Google Translate. I don't know if you remember Google Translate a few years back. It was not so good. That was really hard-coded rules for translation, and now there is a machine learning approach behind it, so it works much better. Well, robotics, I mean, there are a thousand examples. So what are the key drivers behind all this success? A lot of data. Today we have a lot of data. If we look for cat on Google Images, you get millions and millions of photos of cats. Computational power, so we need GPUs to train networks. So you can go to the shop and buy a GPU for 200 euros. Okay? You can train a deep neural network. And of course, a lot of advances in mathematics, in computational data sciences, and so on and so forth. So we are living a lot of exciting times. So we're very, very lucky to be here today. Now, so deep learning has been applied to a lot of classical data. What I mean by classical, well, images, sound signals, maybe volumetric images from medical imaging. So I want to give you a different perspective on how to look at this data. Well, first of all, let's start with the beautiful photo of a cat down there. So that's what we call an image. I encourage you to look at an image as a signal, so colors, painted on a portion of the plane. Okay, so we have a domain which is flat, portion of the plane. And on top of this flat domain, we paint some information. Okay? So we can look at an image as a function going from R2 to R or to R3, if you have 3 color channels. Okay? So if I have 5 different images, a cat, a horse, a car, a sombrero, and a cactus, they have exactly the same domain, right? So it's always flat for all of them. What's the difference? The difference is the information that I right on top of this domain. Similar for sound, the domain is a flat portion of the real line, and we paint information on top of this flat portion of the real line. All clear? Now, what do we mean by geometric data? Geometric data is something that we call non-flat. So mathematically, we say it's a non-Euclidean domain. For example, a social network you can represent as a graph. So each node is a user, and you have an edge to connect two users if they share some relationship, friends or whatever. We have infinitely many ways of drawing a social network on a piece of paper. But we realize that the way we draw the network is not important. So what is important for the network is the connectivity. Who is connected to who, not how is drawn on paper. This means that the domain where the information lives is not flat. The domain is the connectivity itself, is the set of nodes and the set of edges. And then on top of this domain, we might have information. For example, the age of users, or I don't know, how many likes are there between me and you. So that's an information on an edge of the graph and so on. So anything that is non-flat is what I call geometric data. So we have several practical examples. Social networks is just one. A molecule, so we have a molecular graph. And actually the structure of the molecular graph determines the biological function, of course, of the molecule. Or 3D shapes and many others. Okay, so this is what we call geometric data. We want to be able to do learning with this kind of data. So we will see it's not trivial. So I want to identify what are the main things that we have to care about. So just to remove it from the list of problems, one might think that we don't have enough geometric data to do learning. So we said that for cats, we have millions of photos or Google images, while for social networks, we have billions and billions of nodes. So we have enough data to learn something. There is enough data on a social network to predict who I'm going to vote for at the next elections. And so there are a lot of data we can use. We want to use this data. Okay, CNN. I don't think you need me to teach you what is a CNN. I just want to identify what are the main building blocks. Actually, one building block. Why do we call it convolutional? Because of this convolution operation. So imagine a classification task. So we're given a photo of a dog. We have to decide what is the race or species. Race. So we have to identify what is the correct race for this dog. Is it a Siberian Husky? Is it a white wolf? Is it an Eskimo dog? So we don't know. We want the network to identify it for us. And we want to assign a probability, well, a score, telling us how likely it is that that is the correct race. Okay, so CNN, like the most basic architecture we can think of, we have convolutional layers alternated with, well, activations like review and then some pooling later. Okay, so that's not so important. What is important over here, you see this operation, this convolution. Well, we can think of it as a sliding window approach, right? So we have this square window that we slide over the photo from top left to bottom right. And then at each step, we record the correlation between the convolutional filter and the signal below, the signal being the photo itself. So that's the mechanics of convolution. Easy, right? We have it. All right. Now, what if my image is not the photo of a dog, but is, I don't know, do you recognize this shape?
The Earth.
The Earth, very good. So it's not really spherical, as you might know. So it's embarrassingly non-spherical. Did you think it would be such non-spherical shape? It's crazy, right? So you see there is a signal on top of the Earth. There are blue colors, red colors. That's the pressure. That's the local pressure. That's those regions of the Earth. So the pressure, local pressure, is not uniform across all the planet. Now, maybe based on this signal, we might want to predict, I don't know, hurricanes or typhoons, if they're going to show up and when. Or maybe we can have some other information. We want to predict some meteorological, or I don't know, the rise of earthquakes or of tsunamis. There are a lot of cool things we can do. But definitely, we cannot treat this data as an image. So we must be able to do convolutions on this domain. So what is the square window that we shift over this? We don't have a square. Why should it be square to begin with? And what is the top left and bottom right of the sphere? What is the top left? Where do we start? Okay. It turns out, I don't have a slide for this, but it turns out that there exists no convolution for such surfaces. Okay, so this is related to the Poincaré-Hopf theorem. So basically, imagine this: having a convolution means that you have a translation field defined on your domain, and you use this translation field to shift your convolutional kernel. Okay? Of course, for this translation field to exist, it must be non-singular. Okay, so you must be able to shift things at all points on your domain. So imagine that you have a hairy sphere. So imagine this thing with hair, and you have to count the sphere without creating vortices or singularities. It's impossible. Right? So this is also called the hairy ball theorem. You cannot count a hairy ball without creating singularities. I think at least two singularities. So this means, well, this is a picturesque way of saying that you cannot define convolutional spheres. So we have to think of something else. Slightly more complicated example, your 3D shape is this part of the wing of a plane. You want to do your, I don't know, your finite element analysis. You want to predict, I don't know, the forces that the wing is subject to when it flies. I think it's very important. So we don't want the wing of the plane to start shaking like crazy, right? So we want to do some prediction task over here. And this is much more difficult than a sphere. It is a complex geometry. So how do we even define convolution on a complex geometry different from a sphere? So these are the kind of tasks that we want to solve. Very good. So when I say non-Euclidean data, so I will, how much time do I have until 11 or earlier than that?
We started a little bit later. We can do 11, 10, 11. I mean, just we said 40 plus questions, or
I will try to end at 11.
okay, good.
So I will have to skip a few parts, but of course you can ask. So non-Euclidean, non-flat data, we already saw what we mean. So a 3D shape, for example, a statue from Bernini. A graph. Yeah? So this is actually a true subset of the Twitter graph. See, each node is a user. They're connected by friendship relationship. You see there are colors at each node. Red and blue, light red, dark blue. So that's giving me a score of how reliable is that user. Is it somebody that tells true things, or is he someone that spreads fake news? Okay, so how reliable is the user? So we can use this signal to do fake news detection on a social network. So these are the two kind of data we have. One key difference between these two is that over here we have the connectivity of the graph, and we have a signal information on the nodes of the graph. Over here, we don't have any signal. You see, this is pure geometry. So the information is fully encoded in the domain. There is no signal defined on top of this domain. This is very different from images. From images, that would be, let's look at square without anything painted on top. That would be useless, right? So that's a very important difference. What you need to do, again, I'm not going into the details, but we need to replace this notion of a sliding window on an image with something that slides on top of the surface. And in order to do that, well, we don't have a global system of coordinates. When we deal with surfaces, we have to rely upon local calculus, which is what we call differential geometry. Okay, so differential geometry is one of the key mathematical tools we use to do learning on surfaces. So just as an intuition, what's the main point of differential geometry is that you study curved surfaces locally as being locally flat. For example, right now, if I tell you what's the fastest, or what's the shortest path from here to the door, you would tell me, just go straight just walk straight, right? You know very well that this is not flat, right? Because we are on the planet. But locally, at this scale, we can model this as a flat domain. Okay, so that's the main point of differential geometry. All right, so we have to use these tools to define the analogy of the scrolling window, the sliding window you see on the left. We have it on the 3D surface on the right? So we have to be able to do something like this. But this is not well defined because you see on the surface there is no universal notion of right and up. So what direction do we shift? Okay, so a lot of efforts of geometric deep learning, at least at the beginning, was on defining this new idea of convolution. And of course, when I told you that there cannot be a convolution on surfaces, so people have defined analogous ingredients. Okay, so not real convolution, but something that looks like it. So just a couple of examples from 2015, 2016, 2017 actually. So what we defined at the beginning was we defined a local patch. So that's going to be our square window from the images. These are going to be geodesic patches. Geodesic meaning that they are defined on the surface. And well, we just gave a few possible definitions of these patches, and we gave a way of measuring correlations on the surface at all points over the surface. Okay, so the key thing was how to define the geodesic patch. And the important thing is that one of the techniques that we proposed was based on heat diffusion. So imagine that you have this bunny, made of metal, and then you have a very hot needle. You take the needle and you pinch the bunny at one point. So heat is going to diffuse on the surface. There is a very well-known mathematical model for heat diffusion on a surface, and based on this mathematical model, you can define this geodesic patch. And the nice thing about that is that the mathematical model applies as is to structures like graphs. You don't have to have a surface. You can equivalently define heat diffusion on a graph when you don't have a surface. So this is the roadmap of Minnesota. You could do heat diffusion on the roadmap of Minnesota using exactly the same mathematical model. Okay. All right. Now, well, several applications. Let me show you some exciting ones. Do you know this guy? Who is that? Daredevil. So Daredevil is a superhero. He's blind. He can hear very well. And in particular, I think I have. So this is from the movie. I don't know if you can see it well. So this is Daredevil, and he is able to reconstruct the shape of the girlfriend because of rain hitting her face. So from the sound, he's able to reconstruct the 3D surface of the face. This motivated my ERC proposal, so watching the movie. So I said, okay, this is science fiction, looks very cool. I think we can do it. So I investigated a bit. So it turns out the problem has been known in the mathematical physics community for many years, at least since the 50s. So the problem is known as, can one hear the shape of a drum? Can you hear the shape of a drum? So let me show you what it means. This is a drum. Concentrate only on the shape of the membrane. So the shape of the entire tool is not important, but the membrane is ellipsoidal. So you can model how waves propagate from the membrane using a very well-known mathematical model, the wave equation. So this is a simplified version. I don't need you to understand all the mathematics. I need you to understand that there is, can you see the mouse? Yes. So this is the wave equation. You see it is defined in terms of an operator, this delta. This one we call the Laplacian operator. These are the eigenvectors phi and the eigenvalues lambda of this operator. And this is the solution to the wave equation. You see, it's sines and cosines, so waves that oscillate. And the frequency of oscillation is the square root of lambda. So these are the square root of the eigenvalues of the Laplacian. Okay? So hearing the shape of the drum means if you only have the lambdas, this is what you hear, the frequency of oscillation. Can you reconstruct the shape of the membrane? You don't have the eigenvectors, you don't have the operator, you don't have anything. You only have the lambdas, just a few of them, like only 20. Reconstruct the shape of the membrane. Now, this particular drum is very boring. I mean, if I'm able to reconstruct this drum, I don't know. I mean, cool, but not so interesting, right? But these are the kind of drums I'm interested in. Imagine, instead of this flat membrane, you have a drum which is the shape of a lion in 3D. So this is our crazy drum. It is non-flat, but still, if you hit the lion with something, then you produce sound, and that follows exactly the same model that you see over here. Once again, we have the Laplace operator, which can be defined on surfaces. It's called Laplace Beltrami operator. We have eigenvalues, we have eigenvectors. I only have access to the lambdas. I want to reconstruct the shape of the line. So this is what I want to do. Okay, so this was one of the things that I wanted to do in my year C. It was part of the grant. Let me show you a couple of simple examples. So it turns out that you can write a very simple optimization problem that tries to solve this problem of reconstructing the shape from the sound. In the interest of time, I will not explain. If you have questions later, I will. Okay? But I mean, you see the optimization problem is written on top. It doesn't look too complex, right? Of course, it's going to be non-linear, non-convex. It's going to be difficult to solve. Okay? So this is an example. Imagine that I have a drum in the shape of Mickey Mouse, and I only hear the sound. And the sound I hear is the blue eigenvalues you see over here. Now I don't have the shape of Mickey Mouse. I only have the blue eigenvalues. And now from a circle, I try to solve for the shape whose eigenvalues are the same as the blue ones. So this is the optimization process. You see, as the eigenvalues get aligned over here, the circle becomes more and more the shape of Mickey Mouse. So this was our proof of concept that we can, at least in several practical cases, we can solve for the shape of the drum. This is pure optimization, no learning. Next step, if I know the class of shapes that I want to reconstruct, so I know that the drum is going to be the shape of some animal. I don't know which one, but some animal. Then maybe that can help me in driving the optimization process. So we apply a deep learning technique where we train with drums having the shape of animals. So we train with horses, cats, deers, and hippos, I think. And then we try to reconstruct shapes that are different from these 4 animals. Okay? So now what I'm going to show you in this video On the left, you see the eigenvalues. So this is the sound you hear. They are sorted from low frequency to high frequency. Now, the low frequencies usually capture global properties of the shape. For example, if you have very strong low frequencies, then you have a very round shape. If you have very strong high frequencies, then you have very skinny, very high frequency details. Okay, so remember this, because now what I'm going to do in real time, so this is in real time after the network is trained, I'm going to modify these eigenvalues, these frequencies, and on the fly, the shape is reconstructed from the eigenvalues, okay, in real time. So you will see that if I pump up the low frequencies, the shape becomes more round within the class of animals. So you would expect like a fat lion to show up, okay, or some other animal that is round. So see, I'm increasing the high frequencies. Here, look, I'm increasing the low frequencies, becomes a hippo. So I'm going to decrease the low frequencies. See, becomes like a sheep. See, so it is a way of exploring the shape of animals. We didn't see, so this hippo was never seen at training time. Okay, it was one hippo at training time. That was the one that we saw before. That was different from this one. We only had like 4 animals at training. Okay, so all the smooth interpolations, all these other animals that you see as you play with the frequencies, these are all solved from the eigenvalue problem, from eigenvalues to shape. It is a very semantic way of exploring the set of shapes, the space of shapes. We have several other applications of this that I didn't put in this presentation. Let me give you one last application. Then I think I'm going to skip. So let me think. Do you want to hear about adversarial attacks? Do you know about adversarial attacks?
I'm interested.
You're interested? Okay, so let me give you one example. So this is an autonomous car. Autonomous car means that it drives by itself. It is able to recognize road signs, people, so it does all that. Okay. Now it has a visual classification system inside. So when it sees a stop sign, there is this machine learning method that recognizes this as a stop sign. Okay. Now I can perturb the stop sign. So I attach some very carefully planned perturbations. I attach them on the stop sign, and the car recognizes the stop sign as a speed limit, 45 miles per hour. So you can imagine that this can be like can have tragic consequences, right? So what I've done here, I've done an adversarial attack on the visual classifier of the car. This adversarial attack involves solving an optimization problem, okay, which I'm not going to show, but you have to solve an optimization problem. Now, well, this is all well known in deep learning. What about geometric deep learning? So what kind of adversarial attacks can we do on geometry? For example, on a graph, imagine you have an algorithm that predicts from the social network who I'm going to vote for. And I'm one of those guys in the graph. Right? Now it's going to predict that my political preference is Trump. Now I want to fool the prediction system, the machine learning method. I want to apply a very small perturbation, just a very small thing on the social graph, so that the political preference will be mistaken. So what can I do on the graph? I can add 2 friendships, or I can remove 1 friendship from a user, or I can buy a like, or I can sell follows. Okay, so I can do this kind of attacks. As long as I do only a few of them, they're very hard to detect. So that makes them adversarial. And it helps me to fool the prediction system that I'm going to actually go for Cleveland instead of Trump. Okay? So you see that adversarial attacks with geometry makes a lot of sense. With 3D data, what would be an adversarial attack for 3D data? This is from one of our last papers. So imagine you have a pose classifier that tells you, well, that guy is walking. And by the way, this is a true scanning of a real person. Okay, so we actually took a guy in underwear, we scanned the guy, and we asked him to do a lot of poses. And now I want to modify the 3D geometry just a tiny bit, like imperceptibly perturb the 3D data so that the pose classifier is mistaken. So can you see the differences between these two? Just a couple of them? No, maybe the head is a bit moving to the side, the right foot. And I think the guy is a little bit rounder there on the right. See, these are very imperceptible changes. And because of these imperceptible changes, the classifier thinks that this guy is standing instead of making this white step. Okay? So it seems like the network is deciding the pose based on the position of the head or of the right foot. Because if I change those and the prediction is wrong, this also helps us to interpret what the network is doing, right? In terms of open the black box. So this is an optimization example. You see that in order to be imperceptible for 3D data, you want the perturbation to be smooth. So that's what is imperceptible for data. So this is the adversarial attacker that is looking for the smooth deformation that makes the system wrong. You see that it applies smooth deformations and then it stops when the classifier is mistaken. Okay? All right. So just to give you an idea of what is the difference between an adversarial attack on images, where you just change a few pixels, here you don't change a few vertices. You apply a smooth deformation. That's a different concept, different notion. Okay, so one last thing that we did, like in 2 minutes, that was on the cover of Nature Methods a couple of years ago. We applied geometric deep learning to do interesting things with proteins. So we know that proteins are actually geometric domains. As I told you, the 3D structure of protein determines the biological function of the protein. So you see there is a lot of, actually even in the terminology of computational biology, actually of structural biology, that the word structure appears a lot, like the primary structure, the secondary structure, and so on. So they're really structural objects. So our task was, and by the way, so there are several databases online, like PDB. I don't know if you know it. You can look for PDB on Google. You have access to like thousands or hundreds of thousands of 3D structures of proteins, together with their chemical and biological signals defined on top of them. For example, this was the main protease of the COVID-19 virus. So you have access to the 3D geometry of COVID. So it would be cool to do something with this 3D geometry. So one thing we did, we imagine you have some protein, some target protein, and you have a huge database of millions of small molecules. And the idea is that we need to find which of those small molecules binds to the protein. And the binding is defined geometrically. So the binding means that the two surfaces must match geometrically. This is a very difficult problem. So, and people in biology, they do it in the lab. So they take the one by one, they take the protein, they take the potential binder, they try to do the reaction or whatever they do. And if it works, it works, otherwise they pass on to the other one. So we want to do this like in a snap of a finger, like in 1 second for all of them. So we have a geometric deep learning technique that computes like a fingerprint for the protein, computes fingerprints for all the potential binding seeds, and then just compare the fingerprints. Then we can compute the fingerprints because we have CNN-like network on the surfaces. So we did this, and then, well, we moved on with the biological pipeline. We also brought these tests to the lab, so like to do actually the biological experiments, and well, we were able to actually identify binders for these proteins. And this was, I mean, we didn't have to invent anything new. So we just took one of the most basic geometric deep learning pipelines we have, and we applied it as is to the protein. Just nothing special. But this is why I tell you that we want to have a heterogeneous background. We don't want to only be able to do one thing. We want to be as cross-disciplinary as possible. Okay. Let me leave you with one video. So this is an example of an AI that is asked to reproduce the painting on the photo on the left with a set of tools. So I give this learning model a set of brushes, and I ask the learning model to reproduce that as well as possible with the brushes I gave the model. Okay? So you see it's trying to do some artistic rendering of what it sees. It is artistic only because I don't give the model the possibility to be photorealistic. Okay? So this is something that we can do. Something that we cannot do is in 3D. So this is one of the open problems in geometric deep learning, at least from the computer graphics community. Imagine I give you a 3D model, the one you see on the left, and now I want to do some kind of reverse engineering. I want to ask a model to show me step by step the sculpting actions that it needs to apply to recover the 3D model given as input. Exactly the same as with the paintings before, right? But this is in 3D. So it turns out that this is much more difficult task to solve. Well, actually, I see that the video, you're very interested, so I will leave it here for you. And thank you, so I'm open for questions.
Yeah, so thank you for the talk. And is there any questions here? Guys, I know you are not 3D guys, but still you can ask questions, right?
Maybe I can ask one to one.
Yeah.
I was actually, so this is very interesting, but I would like to start with a question from the first section when we talk about building your own path somehow, like the point you raised about, you know, one person have multiple domains. It could be something make you unique. But sometimes I also find it struggling to understand, you know, somehow selling yourself as you have a unified story. Although you do a small little different task, but somehow they are connected. You need to sell it as a whole story about yourself and not too distracted. I also find it not, because I don't know how actually they appreciate if you just sell yourself, I do this, I do that, a lot of things. But if you don't unify them together, somehow people wouldn't really appreciate. I don't know if this is.
I understand. So first of all, that's the main challenge, actually. So if you do semantic segmentation on videos and now you want to do spectral learning on graphs, it's very difficult to marry the two areas. Well, but first of all, you can bring the tools from one area to the other. So you can, for sure, so let me invent just on the fly. You can construct like a graph of connected regions on the video. Then you have a sequence of frames, so you have a dynamic graph that evolves over time, and then spectral graph learning can be applied there. Okay, so these are the ways in which you can glue the two things together. So that's the key challenge. But one important thing is that you don't have to do it necessarily. So I didn't mean that you must explore different domains and put them all together in one. What I mean is that it is very valuable if you construct your background, so your knowledge, if it knows several different things, because it will come the day in which something that you learned here can be applied there. At that point, you will be the only one who can do it. So you don't have necessarily to bring everything together now. Okay, so that's what I wanted to say.
But let's say when you write the proposal and you need to show your profile, I guess maybe there's a necessity to somehow make this type of challenging linkage between different expertise you have.
Yes, but you don't have to force it.
No.
You don't know. So for example, in my proposal, so for example, for the ERC, you only have to show like 5 publications in your CV. And also, I mean, if something doesn't fit, just ignore it. It is like summarized in your overall statistics. Right? So if you have one CVPR paper with 1,000 citations that is not the topic of the ERC, is okay. It's increasing your statistics. So you don't have to force this interaction. And also, you don't have to force the idea. So the idea that you write in your grant proposal, be it ERC or whatever else, must not be forced to bring things together. It must come naturally. Okay, so you don't need to force. You have to think about, you have to like brainstorm a bit, but don't try to force things.
Thanks.
I think this was a very good advice, in my opinion, because I mean, it's like you're an artisan and you're bringing your tools in every workplace, and then you buy new tools and you bring new tools to another work sites, right?
Yeah,
That's good.
It's a very good analogy. Yes.
Any other questions? Yeah.
I have a couple of questions. Comment. So you said that students that patient using eigenvalues large amount for time. So well, it is well known that you cannot so mathematically steer the shape of the graph, so you can easily start the domains in the 2 dimensions which are not isometric, and for which the whole sequence of eigenvalues is exactly the same. So the question is, in order to, for instance, avoid adversarial problems, do you have some guarantee that when you work with some classes of type data sets with some properties, images of animals that are more or less equivalent topologically to both ball or a torus or whatever. Can you say that to have the adversarial effect of the type of small information will be seen by the eigenvalues, and so by all the functions that can be by
Clear.
mixing eigenvalues.
Yeah. Okay, so I see 2 aspects in your question. The first one is, do we have any guarantees that we are able to reconstruct a shape from the eigenvalues without incurring into isospectral non-isometric cases? So first of all, for 2D Riemannian manifolds embedded in R3, there are no known cases of isospectral shapes that are non-isometric. So the examples you're mentioning are either 2D, like 2D, or are like 8-dimensional torus embedded in R50. So they're very exotic examples. So we don't have any guarantee, but at least we don't have any counterexample. Okay, so that's the first thing. So the second aspect is adversarial attacks. So there is a theorem by, I think, Cato, so somebody from perturbation theory, saying that eigenvalues of the Laplacian change continuously with the change in the metric. So if you change the metric continuously, the eigenvalues will reflect this change. And this is true for Riemannian manifolds. So I don't know if this, but this gives me no guarantee that. So this doesn't really help me. That's correct. But at least I don't have any counterexample.
Second question, concerning the most, so the kind of shapes, so the representation of shapes that you consider, are you working with, say, for point clouds or meshes, or so which kind of shape are you considering? Are they structured or not structured, like point clouds? And concerning these, I was wondering if the application of neural networks with say, convolutional neural networks in which you don't put an a priori on the curves, so the curves are learned by the data. Right? And so that my question is, if you maybe some, if someone tried to use some more structured classificator, a neural network in which the first series of layers where some or more geometric, more mathematically rounded features or feature extractors are used, like for instance, curvature or approximate curvature extractors. So from curvature, from explicit curvature, you can reconstruct the geometry, the implicit geometry. And typically, when you work with point clouds, you have point clouds in some ambient space. So it is more natural to do operations in the ambient space, which is different from the case of graphs. In that case, of course, you need to use the implicit geometry.
Okay.
Yeah.
So two questions. The first one is, how do we discretize shape?
Yes.
Okay.
Which are representation that we use.
Okay. So for what? For geometric deep learning or for shape of the drum?
For the geometry.
Okay. So for shape of the drum, as long as you can construct a Laplacian,
Yeah.
you can.
Okay.
So for geometric deep learning, there are different pipelines depending on the discretization of the shape. So for example, for point clouds, there is an entire area that is called learning on point clouds. For meshes, there is an entire area. For splines, there is an entire area. So it matters. It matters. Is that okay?
Yeah.
The first half?
Yeah.
Okay. For about the features.
Yeah.
So that's a great point. So you're mentioning, can we have layers that we inform the learning part better? That's usually the input we give to the network. Usually as input, we don't give the raw X, Y, Z coordinates. We give curvature, I don't know, heat kernels. So we give some kind of handcrafted features. That usually that helps. Yes.
There are any other questions?
Last
The beautiful video. Yes.
Like for example, in this example, person who artist is using additional features like it's not actually curving or it's not actually painting something. It's putting some stuff and extracting some stuff, right? And for example, for a structure, they only extract, they only call something.
Okay, so you're saying the guy over here is not just modeling the sphere, it is adding more shapes. Is that the question?
Yes. So in that case, the person that is searching on just for simple blade or like just curving with a simple blade kind of function.
Okay, so first of all, this one is not an AI.
Yes,
so this is a true person based one.
Yeah.
Okay, right. Okay, so different artists have different styles of modeling. Okay, so this guy in particular, I know him. He decided to bring extra materials that makes the modeling easier. But it is possible. So that shape has sphere topology. So it means that there exists a homomorphic transformation that brings the sphere to the face. Okay. But apparently, it is much easier to to add more pieces, like Lego pieces. So maybe the general question is, what would be the correct paradigm to emulate with an AI? So do you want the AI to solve for the homeomorphism, or would you like the AI to solve for the shape composition that makes things easier? And these are the open questions that we have today. Okay, so I don't have an answer.
Maybe from home, somebody.
I think there is another one.
Okay.
Yeah. You said that you are using a feature vectors from a simple feature extractor. And how descriptive is feature extractor in the sense of folding? Like you can connect in different angles, right?
Right. So, okay. So first of all, well, this is not folding. Folding is a different problem. Like, so you're asking, basically, you're asking if the machine learning model is invariant to rotation. Is that your question? It is. So it is purely intrinsic. So it doesn't matter which orientation the protein is seen. Time or this is fully intrinsic. So it's rotation invariant.
How it is managed to do this rotation invariant? Because you have this local reference somehow pre-computed, or I don't know.
So okay,
What's the magic?
Let me give you a very simple example. Imagine that you have a 3D model, okay? And I don't know, imagine that you have a point and the neighboring points.
Yeah.
Now imagine that you have a normal vector at each point. So if your descriptor is the sequence of normal vectors, of course, when you rotate the shape, the descriptor must change. So that's not rotation invariant. But if instead the normal vectors, you compute the inner products between normal vectors, so you compute all the dot products, the angles between them, even if you rotate the shape, the angles between vectors do not change. So that's rotation invariant. So the model we have does something like that, not with rotational, not with normal vectors, with some other quantity.
Okay. Thanks.
I think we took quite a few questions. I don't know if you have others, but otherwise we can thank the speaker.
Thank
And
you.
thank you for
having me.
having me.
Thank you.